We will begin our discussion by looking at the straight line. First, we will look at deriving the equation of the straight line using two coordinates. We will then look at deriving the equation of the straight line from a set of coordinates as well as the gradient. We will then move more into the gradient. First, we are going to get the equation of the straight line from two coordinates. I'm going to use coordinates A, which is 5 and 4, and coordinates B, which is -2 and 5. And I'm going to get the equation of that straight line. Now let's just draw that out just to see what sort of straight line we're looking at. A's coordinates is x is equal to +5, y is equal to +4, so it's going to be over there. B is x is equal to -2, y is equal to +5. So that's going to be somewhere over there. Alright, so we're looking at that graph over there, or that straight line rather. That's B and that's A. To get the equation of a straight line using two coordinates, I'm going to start off by saying y is equal to mx plus c. Now this is the standard equation of our straight line. The next thing I'm going to do is I'm going to get my m value. Now a golden rule about straight lines is that we are very concerned about the gradient. Obviously we're concerned about everything else, but the gradient is usually our starting point. The gradient tells us a lot about our graph. The gradient in this case is going to be y2 minus y1 over x2 minus x1, which is equal to y2 minus y1, 5 minus 4, over x2 minus x1, which is -2 minus 5, which is going to give us a gradient of 5 minus 4 is 1, -2 minus 5 is equal to -7. That means that our gradient is -1/7 or 1/-7, it's the same thing. That means that y is equal to -1/7 x plus c. Notice I went back to that form, except I now have m. Y and x are fine. In a straight line we are alright with having y and x. The problem is c. We want c to be a value, to be a number, as opposed to just a variable. In order to solve for that, I'm going to substitute any point in. Now I'm going to substitute both points in, and I'm going to show you that it's going to give the same answer. First, let's substitute a in black. Instead of y, we're going to put 4. 4 is equal to -1/7. X is 5 plus c. That means that c is equal to, now all I'm doing is keeping c on this side, taking everything across to the other side, but I'm flipping it. So that's going to be 4 plus, because that will become positive, plus 5/7. 1/7 times 5 is 5/7. Problem is, this is 4/1 plus 5/7. That's the same as 28/7. I just multiplied it by 7. 4 times 7 is 28, plus 5/7, which is equal to 28 plus 5 is equal to 33/7, positive. That means that my equation now reads y is equal to -1/7x plus c, but instead of c it's plus 33/7. If you want to neaten this out, you can say 7y is equal to -x plus 33, but there's no need to do that. You can leave it in this form. That means that this point here, the c value, or the y-intercept rather, is going to be at positive 33/7, and an x value of 0. And its gradient is negative sloping, -1/7. Now that's substituting point A in, which I did in black. I'm going to show you that point B will give us the same answer You don't need to substitute both points in though. I've got y is equal to negative 1 over 7x plus c. I'm now going to substitute 5 in place of y is equal to negative 1 over 7 multiplied by negative 2 plus c. That means that c is equal to 5 minus, because minus times a minus is positive, take it to the other side is going to make it negative 2 over 7. Again, that's over 1, so I've got to simplify it. That's going to become 5 times 7 is 35 over 7 minus 2 over 7, which is equal to 33 over 7, which is going to lead to the same equation. Now we are going to look at coming to the equation of a straight line using a gradient and a set of coordinates. In this case, the gradient I'm going to use is negative 5, and the set of coordinates I'm going to use is 2 and negative 8. Not a difficult one to do. In fact, this is even easier than the previous example, because in the previous example we used our 2 coordinates to get the gradient. That means that our equation reads from the start y is equal to negative 5mx plus c. To get c, I'm going to substitute any point that I have. I've only got one point, so I can only substitute that point in. Minus 8 is equal to negative 5 times 2 plus c, means that c is equal to minus 8. Negative 5 times 2 is positive 10. Negative 10, sorry, taken across becomes positive 10. That means that c is equal to positive 2. That means that y is equal to negative 5x plus 2. Which means that our graph is going to be very negatively sloping, very steeply sloping. And it's going to cut the y-axis at positive 2. I'm not going to fill in any more information about that. That's just to show you what that graph would more or less look like. Also, we know that it's passing through the point x is equal to 2, y is equal to negative 8. So that's going to be negative 8 and possibly 2. Something like that. The big thing you need to note is that if we had our gradient, we just needed one point to get our c value. Once we got our c value, we went back to the standard equation. Now let us take a quick look at moving from the equation of a straight line onto the coordinates. I'm going to use the example y is equals to 3x minus 4. Sketched on a graph, it looks like this. If I need to move to any set of coordinates, I am going to have to plug in the corresponding values. For instance, if I'm looking for the y value when the x value is equals to 5, how will I do that? It is actually quite an easy one. All I'll do is I'll substitute that x value of 5 into my equation y is equals to 3x minus 4. That means that my corresponding y value will be equal to 3 times 5 minus 4, which is 15 minus 4, which is equals to 11. In most forms of analytical geometry, the easy way of getting the corresponding coordinate is always to just plug in the value that we do have into the formula. I want you to have a go at the following examples. Press pause on your DVD player, and when you return we'll go through it together. And I told you that we have an x value of 2. What is the corresponding y value? Now in order to do this, it's actually quite easy. All we're going to do is substitute this x is equal to 2 in. That means that y is equal to 3 times 2 minus 7, which is equal to 6 minus 7, which is equal to negative 1. That means that our coordinates there are x is equal to 2, y is equal to negative 1. And I also told you that our y value is equal to -6, and I want the corresponding x value. Again, easy to do. All I do is substitute that -6 into the y. That means that -6 is equal to -2x plus 5. Take the -2x across to make it positive 2x is equal to plus 5 plus 6, which is 11. That means that x is equal to 5 plus 6, which is 11 over 2. That means that our coordinates here are 11 over 2 and a y value of -6. Let us now take a closer look at the gradient. I'm going to start with two parallel lines. The first graph I'm going to sketch on a Cartesian plane is the line y is equals to 3x minus 4. On the same set of axes, or on the same Cartesian plane, I'm going to sketch the graph y is equals to 3x plus 2. Notice something about these graphs. They are parallel. What else can you see about the graphs? They both have the same m value or the same gradient. They both have a gradient of 3. That means that both of these graphs have a slope of 3. Hence they are parallel. That brings us to the first rule when dealing with gradients. When lines are parallel, the gradients are equal. Alternatively, when the gradients are equal of two lines, those two lines are parallel to each other. Let us now look at perpendicular lines. Remember, a perpendicular line, or rather perpendicular lines, are when lines form an angle of 90 degrees between them. We are going to use basic trigonometry to define a rule we can use for when we are working with lines that are perpendicular to each other. We are now going to look at the relationship between gradients of lines that are perpendicular. Now I've drawn a triangle ABC in here with AB the hypotenuse and CA being perpendicular or right angled with CB or BC. Let us start. I'm going to start by proving that this is a right angled triangle. You don't need to do that whenever you're working with perpendicular gradients. I'm just doing that to show you that this is in fact a right angled triangle. The way we're going to do that is use the distance formula. The distance CB is going to be given by y2 minus y1, which is minus 1 minus 1, which is minus 2 squared, which is positive 4, plus x2 minus x1, which is 3 minus 1 squared, which is just 1. That means that the distance CB is given by square root 5 or root 5. Distance CA is going to be given by y2 minus y1, which is 2 minus 1, which is 1, squared is 1, plus 4 minus 2, x2 minus x1, 4 minus 2 is 2, squared is 4, which is also going to give us root 5. AB is going to be given by square root of y2 minus y1 minus 1 minus 2 is going to give me minus 3, squared is positive 9, plus 3 minus 4 is negative 1, squared is positive 1, so it's 9 plus 1, which is equal to square root of 10. If this is in fact a right angled triangle, it should follow that AB squared is equal to AC squared or CA squared. Let's work with CA squared plus CB squared. The reason for that is that in a right angled triangle, the hypotenuse squared is equal to side A squared plus side B squared. AB squared root 10 squared is equal to positive 10. CA squared is equal to 5 plus CB squared is equal to 5. 5 plus 5 is equal to 10, which means that this holds true, that ABC is in fact a right angled triangle. That means that AC is perpendicular. AC, we now know, is definitely perpendicular to CB, which means that that's a right angled triangle. Now let's look at the gradient of AC. The gradient of AC, or CA, is going to be given by y2 minus y1, which is 2 minus 1, over x2 minus x1, 4 minus 2, which is equal to 2 minus 1 is 1, 4 minus 2 is 2, so our gradient there is positive a half. Our gradient of CB is equal to y2 minus y1, which is minus 1 minus 1, over x2 minus x1, which is going to be given by 3 minus 2, which is equal to negative 2 over 1, or negative 2. Now remember, at the outset I said that we are looking for the relationship between the gradients of perpendicular lines. It doesn't seem that there's a relationship just yet, does it? 1 over 2 and negative 2, the 2's are the same. But watch this. If I multiply these two gradients, it gives me an answer of negative 1. And you're going to find that is a general rule for working with gradients that are perpendicular. The one gradient multiplied by the other gradient is equal to negative 1. That means that if I have a gradient of negative 3 over 4, what is going to be my gradient of the perpendicular line to that line that has the gradient of negative 3 over 4? We don't know, we just know that it's the perpendicular gradient, but we know that it has to equal negative 1. So to get rid of that times negative 3 over 4, we're going to say multiplied by negative 4 over 3, which is going, by the way, that was negative 3 over 4, which is going to give us an answer of positive 4 over 3. So the perpendicular gradients multiplied by each other are always going to give us an answer of negative 1. Now there is an easier way of doing this. We just look for the negative inverse of it. For example, if our gradient is 2 over 5, our perpendicular gradient to that line will be negative 5 over 2. If our original gradient was positive, let's say negative 3, our perpendicular gradient, now that's negative 3 over 1, that means that our perpendicular gradient will be positive 1 over 3. All we're doing is swapping it around and changing its sign, either from positive to negative or negative to positive. And that there is the relationship between gradients of lines that are parallel. Now let us look at theta, the size of angle theta of CB. So far we've looked at the angle of inclination theta of a line that has a positive gradient. Now let's work at that one. The angle of inclination of CA, remember m is equal to tan theta, but we know that our gradient of CA is 1 over 2 is equal to tan theta. That means that theta should equal second function tan of a half. Second function tan, I always say second function tan, it's just the inverse tan function of 0.5, which is going to give us an answer of 26.6 degrees. That is the angle of inclination of CA. But I asked for the angle of inclination of CB. Now think about this. If I draw a line parallel to CA over there, wouldn't that also have 90 degrees? Wouldn't that also be 90 degrees or perpendicular to CB, because it's parallel to AC or to CA? Also, wouldn't its angle of inclination be the same as the angle of inclination of AC? Yes? That means that the total angle of inclination of CB is going to consist of that small angle of inclination, which is 26.6 degrees, plus the angle of inclination, or rather plus the perpendicular or the 90-degree angle over there, which will give us an answer of 116.6 degrees. Let us see what happens when we try and work it out in this form. M is equal to tan of theta. Remember, we are now looking for for theta, or angle of inclination of CB. That means that tan theta is equal to CB's gradient is -2. That means that theta is equal to the inverse function tan of -2, which is going to give us an odd answer. It's going to give us an answer of -63.4 degrees. Now the reason it does that is because our scientific calculators only work in one quadrant, quadrant 1. Alternatively, if we have something like this, they're going to stretch themselves to work in another quadrant, which is quadrant 4. However, you can see here that that angle is really in quadrant 2. Wouldn't that be the same as 180 degrees minus 63.4 degrees? Let us look at what answer that gives us. That gives us an answer of 116.6 degrees. It doesn't matter which way you look at it. My preferred way of doing this, working out the angle of inclination of the negative gradient, would be to first work out the angle of inclination of its positive gradient and then add that to 90 degrees, and that will give us the total angle of inclination. Let me give you another example of that. Let's imagine that we've got two lines. The first line is y is equal to 3x plus 5, and the second equation is the line y is equal to -1 over 3x plus 2. Now y is equal to 3x plus 5 is going to look something like that, cutting it at 5, and y is equal to -1 over 3x plus 2 is going to be a line that looks very much like this, and that's going to be 90 degrees. To work out this angle of inclination, the negative gradient or the negative angle of inclination, I'm going to start by working out its opposite, or rather its perpendicular sort of partner. That means that I'm going to work out m is equal to tan theta, but the m value I'm going to use is not the -1 over 3, but rather the positive 3. That means that theta is equal to the inverse function tan of 3, which is equal to 71.6 degrees. But remember, I was looking for this angle here. So I'm going to add that to 90 degrees, which is going to give me 161.6 degrees. Alternatively, I was looking for that theta originally. Let's ignore the perpendicular line altogether. We could have said tan theta is equal to -1/3. That means that theta is equal to the inverse function tan of -1/3, which is going to give me -18.4 degrees. I add 180 degrees to that, which is going to give me an answer again of 161.6 degrees, rounded off to 1 decimal place. Let's have a go at one more example. Let's say we have a straight line with the equation y is equal to -1 over, in fact, let's not use this 1. Let's say y is equal to -2/3x plus 5. And what is the angle of inclination? Now -2/3x plus 5 is going to look something like that. We are asking what is theta. To get theta, we're going to say m is equal to tan of theta. Now if we use my method, the 90-degree addition way, I'm going to look not for a gradient of -2/3, but I'm going to say tan of theta, or rather theta is equal to the inverse function tan of the positive gradient, or the perpendicular gradient, which is going to be +3/2, plus 90 degrees, which is going to equal, I'm just going to work that out on the calculator, inverse function tan of 3/2 plus 90 degrees is equal to 146.3 degrees, rounded off to 1 decimal place. The other method would have said theta is equal to inverse function tan of -2/3 plus 180 degrees, which is equal to the inverse function tan of -2/3 plus 180 is equal to, again, 146.3 degrees, rounded off to 1 decimal place. It doesn't matter whether we did the inverse gradient or the positive gradient plus 90 degrees or the original gradient plus 180 degrees, it both gives us the same angle. We are now going to move into some exercises. You will notice that most of the exercises include work from the previous tutorial. As I said in the previous analytical geometry tutorial, no analytical geometry works in isolation. You have to use different concepts together in each question. The first few are very basic. They do deal with gradient and finding the equation of the straight line. Thereafter, there are some cumulative examples. Press pause on your DVD player, and when you return, we'll go through it together. The first example I gave you to do had this graph over here with points A and B, M being the midpoint. We started off by saying, find the length of AB. To get the length of AB, we're simply going to use the distance formula. AB is equal to y2 minus y1 squared, which is going to be 6 minus 2 squared, plus x2 minus x1, which is 5 minus 1 squared. And that's going to give us 6 minus 2 is 4, squared is 16, plus 5 minus 1 is 4, 4 squared is equal to 16. That means that our answer is root 32. If you want to simplify that further, you can. 16 goes into 32 2 times, so that's 16 times 2. Square root of 16 is 4, root 2 stays as root 2. That means that the distance AB is equal to 4 root 2 units. Let's put that answer in over there. The next thing we're looking at is the coordinates of M, which is the midpoint of AB. To get our x value, we're going to say x2 plus x1, which is 5 plus 1, divided by 2. And to get our y value, we're going to say y2 plus y1, also over 2. That means that the coordinates of M are 5 plus 1 is 6 over 2 is 3, 6 plus 2 is 8 over 2 is 4. That means that the coordinates of M are x is 3, y is equal to 4. The next thing we're looking for is the equation of AB. To get the equation of AB, we're going to start off by saying y is equal to mx plus c. We're going to start by looking at our M value. M is equal to y2 minus y1 over x2 minus x1, which in this case is going to be 6 minus 2, y2 minus y1 over 5 minus 1, which is equal to 6 minus 2 is 4, 5 minus 1 is 4. That means that our gradient is equal to positive 1. That means that y is equal to 1x, or just x, plus c. To get our c value, we then substitute any point that we have. If you want to be complicated, you're welcome to substitute 5 and 6 in. 1 and 2 is a lot easier to sub in though. That means that 2 is equal to 1 plus c. That means that c is equal to 1. Take the 1 across, 2 minus 1 is 1. That means that our equation reads y is equal to x plus 1. And that's number 3. The fourth one asked for the equation of the perpendicular bisector of AB. Now we are looking for the equation. Let's read it out carefully. Equation of the perpendicular, I said perpendicular line. In your workbook it says perpendicular bisector through M. But let's just break that up. Perpendicular bisector through M. I spelled through badly. Equation of the perpendicular. Perpendicular tells you that the gradient of that line is going to be perpendicular, or is going to be the negative opposite of AB. Bisector. The word bisector, bi means to, sector cut. Cuts it in two or cuts it in half. If it cuts it in half, it always has to run through M. So we know that the equation of AB is y is equal to x plus c. Of our new equation, we're going to have y is equal to if our original gradient was 1, our perpendicular gradient is going to be negative 1, because that's 1 over 1. Flip it around, it's still 1. and change the sign. That means that our new equation will read y is equal to negative x plus c. To get c, we substitute any point that we have in. We've only got one point, and that's the point that it passes through, which is m. X is equal to 3, y is equal to 4. That means that 4 is equal to negative 3 plus c. C is equal to 4 plus 3, which is 7. That means that our equation will read y is equal to negative x plus 7. And that's number 4, the equation of the perpendicular bisector of AB. The second one I gave you to do read, find the value or values of A if P is equidistant from A and B. Equidistant means that the distance between PB is equal to the distance between PA. Because we're looking at equidistant, we are going to be using our distance formula. We've got an A value, which is our X value of P, and we've got the Y value of 4. So let's look at the distance of PB. PB is going to be given by square root of y2 minus y1, which is going to be 3 minus 4 squared, plus x2 minus x1 squared. That's going to give us 3 minus 4 is negative 1, squared is positive 1, plus, let's just leave that for now as 3 minus a, all squared. That's PB. PA is equal to square root of minus 1 minus 4 squared, plus x2 minus x1, which is minus 2 minus a squared, which is equal to minus 4 minus 1, or minus 1 minus 4 is minus 5, squared is 25, square root of minus 2 minus a, all squared. Leave it at that. Now we are told that P is equidistant from A and from B. That means that PA is equal to PB. Now we know that PA is that, and we know that PB is equal to that. That means that PA, or rather PB, which is square root of 1 plus open bracket 3 minus a squared, we know that that is equal to square root of 25 plus minus 2 minus a squared. Right? That's because they're equidistant. PA, all we've done is said that PA is equal to PB. We've got square roots on both sides, nothing else, so I can square both sides to get rid of this square root sign. That means that 1 plus 3 minus a squared is equal to 9 minus 6a plus a squared is equal to 25 plus 4 plus 4 plus 4a plus a squared. That's minus 2 minus a squared. Because I've got a squareds, actually I don't need to take it all across to one side. Plus a squared on this side cancels with the plus a squared on that side. Take the a's across, so I'm left with minus 6a minus 4a is equal to 25 plus 4 minus 1 minus 9. That means that minus 6a minus 4a is equal to minus 10a is equal to 25 plus 4, which is 29. 29 minus 9 is 20, minus 1 is 19. That means that a is equal to negative 19 over 10. That's that point over there, negative 19 over 10. That's the x value. And that does make sense because negative 19 over 10 is the same, or more or less this, it is the same as negative 1.9, which we can see is just slightly below negative 2. So that holds true. Number 3 gives us this graph over here, PQ. Q is the coordinates A and B, R and S. P, R and S have all got their coordinates. They ask us to find A and B, which are the coordinates of Q, if PQ is perpendicular to RS and Q is equidistant from R and from S. Now let's start with this equidistant bit, because that looks like the more difficult one to do. If it is equidistant, it means that QS is equal to QR. That means that QS squared is equal to QR squared. QS squared, remember using the distance formula, is going to be y2 minus y1, which is b minus minus 4, or b plus 4 squared, plus x2 minus x1, which is going to be a minus 2 squared, and that should be in the square root, but remember we're squaring it to get rid of the square root. Similarly with QR, we're going to have b minus 3 squared plus a plus 4 squared. I'm not going to simplify this out. Actually, I am going to simplify this out. B plus 4 squared is going to give me b squared plus 4b plus 4b plus 8b plus 16 plus a squared minus 4a plus 4 is equal to b squared minus 6b plus 9 plus a squared plus 8a plus 16. I've got a b squared on both sides of the equation. They cancel each other out. I've got an a squared on both sides. They cancel each other out. I've then got 8b plus 16. Take all the b's and a's to one side. So 8b minus 6b taken across becomes plus 6b. 8b plus 6b is equal to 14b minus 4a minus 8a, when I take it across, will be minus 12a, plus 16 plus 4 is going to give me plus 20, taken across to the other side is equal to plus 9 plus 16 is plus 25, plus 25 minus that 20 is going to give me plus 5. That means that 14b minus 12a is equal to 5, and that's my first equation. I've got two variables, hence I'm going to have to solve simultaneously. Do I have another equation? Thankfully I do. They tell us that PQ is perpendicular to RS. That means that my gradient of the one will have to be the opposite negative gradient of the other. Let's just erase this and keep this equation. So we've got our first equation being 14b minus 12a is equal to 5. That's equation 1. Now, our gradient m of rs is equal to y2 minus y1, which is minus 4 minus 3, over x2 minus x1, which will become 2 minus minus 4, 2 plus 4. Minus 4 minus 3 is minus 7. Over 2 plus 4 is 6. So our gradient of RS is negative 7 over 6. That means that our gradient of PQ has to equal 6, positive 6 over 7. But we know that the gradient of PQ is going to be given by y2 minus y1 over x2 minus x1. Minus minus 3 is plus 3, minus minus 4 is plus 4. That means that 6 times a plus 3 is equal to 7 times b plus 4. All I've done is I've cross multiplied. That means that 6a plus 18 is equal to 7b plus 28. 6a plus 18, what I'm going to do here is I'm going to get it in terms of 6a. That means that 6a is equal to 7b plus 28 minus 18, which is plus 10. And that's my second equation. 6a is equal to 7b plus 10. Remember, I got to this using the gradient of the one being the opposite gradient of the other. Now, what I'm going to do now is use these two equations simultaneously to get my values of a and of b. Here I've got 6a is equal to 7b plus 10. Let's convert that one. That minus 12a, take the 12a across and the 5 across to the other side. That means that 14b minus 5 is equal to positive 12a. Swap it around and divide by 2. That means that 6a is equal to 14 divided by 2, which is 7b minus 5 over 2. There is going to be a slight problem with this. I've now got two equations in the form 6a is equal to. The problem with this is that if I substitute that in place of that, I'm just going to cancel my 7b's out altogether. So unfortunately this one is not going to work out like that. What I think I'm going to do with this one rather is, let's rather get it in the form 7b is equal to 6a minus 10. That means that 14b is equal to 12a minus 20. Again, if I substitute it in, I'm going to cancel. Now I've just realized that because Q is equidistant from R and S, and that is perpendicular to that, there could be a number of different A values. We could have A values there, we could have A values there, and that would all be equidistant. We could even have values there or there. So, in effect, there is a relationship between A and B, which would be the gradient of PQ, but there are no fixed values of A. Let's imagine that I had to tell you that the value of A was 2. You then substitute it in there. That means that we'll have 6 times 2 is equal to 7b minus 5 over 2. That means that 6 times 2 is 12, times 2 is 24 is equal to 7 times 2, which is 14b minus 5. That means that 14b is equal to 24 plus 5, which is 29, which means that b is equal to 29 over 14, almost equal to 2 as well, right? Almost, not exactly. For different a values, there are going to be different b values, but there's a whole number of different a and b coordinates that we can come to. That's why when we try and solve this simultaneously, all we'll ever be doing is eliminating the a's or eliminating the b's. The next question asks, does PQ bisect R S. Does PQ bisect RS? Well, let's look at the point of intersection M. Is M the midpoint of RS? Or rather, does the midpoint of RS fall on PQ? Now we've got our gradient. We know that our gradient of RS was given by minus 7 over 6, which means that our gradient of PQ we know is 6 over 7. That means that the equation of PQ reads y is equal to 6 over 7 x plus c. To get our c value, substitute the only real point that we have, because we don't have that. That means that minus 4 is equal to 6 over 7 multiplied by negative 3 plus c. C is equal to minus 4 plus, because that becomes negative, taken over becomes positive. 6 times 3 is 18 over 7, which is equal to negative 28 over 7 plus 18 over 7, which is equal to negative 10 over 7. That means that the equation of PQ is equal to y is equal to 6 over 7x minus 10 over 7. And that's the equation of PQ. The question I'm asking is, does it go through the midpoint of RS? Now the midpoint, the coordinates of M, the midpoint of RS are going to be given by x2 plus x1, which is 2 plus negative 4, which is equal to negative 2 divided by 2 is negative 1, and the y value is negative 4 plus 3, which is negative 1 over 2, negative 1 over 2. Does this point fit in there? Well, let's test it out. If this point fits in there, if I substitute this in place of x, y should give me that. Y will equal 6 over 7 multiplied by negative 1 plus 10 over 7, which is going to be negative 6 over 7 plus 10 over 7, which is negative 4 over 7, which is not negative 1 over 2. Hence, the midpoint of RS is actually going to be somewhere over there. PQ does not go through the midpoint of RS. And that brings us to the end of the second analytical geometry tutorial. In the next tutorial, we will be looking at triangles and other basic shapes related to analytical geometry. Please note that the entire third tutorial deals with work covered in this tutorial and the previous tutorial, which dealt with basic analytical geometry. Make sure that you are able to do the exercise that I've left for you in the workbook before progressing on with the next tutorial.